Well, friends, greetings from Total Output Power Solutions. Welcome to this series of performance improvement of AFBC boilers. So today we have a theme of every loss can be a gain, and with this theme we start our session for the excess air or the air ingress. So air ingress in boilers, we will discuss about the probable points of ingress and the effects on the boiler. I am Manohar Tatvavadi from Total Output Power Solutions, Balewadi, Pune. So we first of all discuss what is air ingress. Many boiler users are ignorant about the air ingress in their boilers. In this video, the probable locations and the detrimental effects of air ingress are brought out. Reality is that some of our fellow boiler users are still carrying losses with air ingress. Now we'll see what is air ingress. In a balanced draft furnace, the forced draft, secondary air, primary air fans, they pump the air into the furnace. The flue gas produced is drawn through the boiler by the induced draft fans. Hence, the furnace and downstream the furnace, the boiler is under negative pressure. Thus, if some leakage spots are there, the ambient air is drawn through such openings. This is the schematic of the ABC boiler. You can see the furnace, the fuel burns inside the furnace, and the flue gases they pass from furnace to the economizer, and through the economizer then they go to the air preheater and then to ID fan. So the whole path from furnace to ID fan will be the downstream of the furnace. The probable air ingress points as can be found out. In the balanced draft furnace, there are several areas for ingress of air. The possible locations, they include the rooftop where superheater coils penetrate in, membrane walls where the convection banks penetrate, roof tubes termination in steam drum, boiler bank tubes terminations in side, front and rear of steam drum, boiler bank tubes terminations in side, front and rear of water drum, between the boiler bank hopper and water drum. Then hopper manholes, hopper isolation gates and flanges, woven out rotary ash feeders, failed fabric expansion joints, corroded metallic expansion joints, incomplete fastened flange joints, improper roped flange joints, refractory wall cracks, then eroded or corroded air preheater tubes, economizer casing joints, access doors, roof panel to side walls side joints, water drum to bank casing plates, nose panel to water drum termination, soot blower openings, gas pressure tappings, leaky view holes, boiler bank casing plate joints, and many more locations can be there, but the identified these are the locations. Then locating the air ingress. It's also a task how to locate the air ingress. Now there can be many possible locations from where the air leaks in. An easy way in a solid fuel fired boiler is of course the ash would leak out in locations where the air goes inside. You can always see the fresh ash spillages around the air ingress points. A temperature mapping of the boiler outside walls also may give a clue for the air ingress points. To locate the air ingress points, the smoke test should be done. Another way is to carry out a flame test with ID fan running and arresting the air leakage. Having identified the leak points, measures are to be taken to arrest the air ingress. Some air ingress points are simply rectified, they are simple to rectify, but at some locations the design may be faulty, for which one has to call up the designer or the consultant for help. The seals may call for a better contemporary design. The design may need for a review from the boiler thermal expansion point of view. Now, why is this air ingress? By virtue of boiler configuration, openings are to be made in the boiler enclosures or water wall enclosures. If a seal is improperly designed or improperly erected, the seal may fail and develop air ingress. The seals may have been erected properly. It is possible that some of the seals are not taking care of thermal expansion or the service conditions, and thus leakage may develop. One step further, the repairer has not put back the seals as per design, since he may not have the blueprint of the original design. Now we talk about the effects of air ingress. The first is the high unburnt carbon in fly ash. It is general practice to trim the air flow based on the oxygen indication from the flue gas. When the air ingress is present, the oxygen indicator indicated by the oxygen meter, online oxygen meter, would mislead the operator. The furnace runs into substoichiometric condition. This ultimately leads to increase in unburns. The effects. Second one, increased fuel consumption. The air ingress downstream the flue gas path leads to increased heat loss in the chimney. To compensate for the heat loss, one has to feed more fuel. So the fuel consumption increases. Then overloading of ID fan. When we experience that the ID fan is falling short of capacity, we tend to invest in new ID fan. We start with the fan vendors for increasing the fan capacity. In many cases, the second ID fan is opted with higher capacity with the assumption that the existing ID fan is short of capacity. In some cases, even the second ID fan may also prove useless as the air ingress persists and the furnace still goes with positive pressure. The boiler operating expenses increase due to additional power consumption. Then there is backfire in the furnace. The backfire is continuously experienced. The ID fan damper is at full open position. The operator has no option except to continue with the problem. This unsafe condition persists. The insulation of the boiler is spoiled on this account. Soot is seen around the furnace access doors. When secondary combustion in the superheater zones, the furnace begins to starve when the air egress is more from the roof seal box or the convection superheater seal box. This ingress air allows secondary combustion of volatiles. The superheater temperature becomes uncontrollable. Particularly at the time of load variation, the fuel feeder RPM is regulated by the operator and he finds that the superheater steam temperature rises faster than the pressure. This is seen more in boilers fired with biomass fuels. Then secondary combustion in the boiler bank hoppers. When the air ingress is present downstream, the unburnt fuels burn at the boiler bank ash hoppers since the furnace is at substoichiometric conditions. The unburnt fuel travels downstream instead of completely burning in the furnace. The ash hoppers get distorted due to secondary combustion. Then ash blockages in the boiler bank baffles. When the ash is not fully burnt in the furnace, the flow ability of ash comes down. The ash particles now contain fuel particles which may be fibrous or irregular in nature. Thus, the fuel and ash settle at every possible location where the surfaces are less inclined or flat. The ash does not flow freely and thus ash accumulates at baffles. Whatever the draft is set, the ash does not flow due to nature of the accumulations. Then ash blockages in hoppers. Carryover of fuel particles to ash hoppers would lead to a combustion in ash hoppers. Lumps form due to static combustion. We try to poke the ash drain pipes, but the situations repeat often. The combustion is not complete at the furnace and hence the troubles. Excess de-superheater spray. The furnace is designed to be hotter as the combustion is to take place here. The furnace dimensions are so chosen to achieve the necessary residence time for the fuel particle to burn fully. Starvation occurs when the air can bypass the furnace and enter the flue gas downstream. Under such conditions, the combustion zone shifts to superheater section. Simultaneous combustion and heat transfer at superheater section leads to excess steam temperature. Now if excess capacity is available in the spray control valve, we tend to spray more. More spray may lead to solids added to superheater section. The solids left behind in the superheater lead to deposit related failures in boilers. More the spray, the turbine blade deposition is experienced in the turbine. Clinkers formation in the furnace. The furnace temperatures are controlled by the incorporating necessary heat transfer surface and by admitting required excess air to cool down the gas below the ash melting temperatures. The excess air cannot be given in the furnace when the ID draws the leakage air downstream. Refractory furnaces get coated with ash deposits. Honeycombing of ash accumulations is seen in some agro-waste fired boilers. Refractory rooftops eventually collapse due to increased weight. High furnace temperatures and refractory walls caving in. The excess air when not given in the furnace temperature exceeds the design gas temperatures. When the fuel does not have much of ash, the furnace temperatures they go up. The refractory walls expand unusually, leading to furnace walls caving in. Then furnace doors failure. Furnace doors in balanced draft furnaces are refractory lined to thickness of not more than 250 millimeters. The doors get cooled by the outside ambient air present around the door. When the furnace is under positive pressure, the ambient air is not present near the vicinity of the doors. Then the doors bulge. The manhole frame and manholes distort due to heat. We think the doors fail due to material defect. Then furnace refractory failures. The refractory totally collapse, often since they lose strength at higher temperatures. The high temperatures are experienced when the excess air is less and the furnace temperatures go up. The refractory design would be unstable at higher service temperatures unless the design is modified for the new service conditions. Furnace seal plates, they are running hot. In many furnaces, particularly in small boilers, are provided with casing plates to prevent air ingress. When the furnace temperatures are not controllable due to insufficient excess air, the casings run hot. When the furnace goes positive, the gas reaches the air gap between the casing plate and the refractory. The flame and or the smoke is seen, particularly in gas-fired boilers. The gas burns inside the casings. The most important is again the fly ash nuisance around the boiler. The fly ash poses a great nuisance, not only harming the eyes but also the lungs. The boiler house becomes shabby. The industrial standards go down in front of your customers. The cost for cleaning the boilers goes up and the boiler downtime increases due to this. Now during the maintenance, hours are to be allocated only for cleaning. So these are all the effects of the excess air ingress in the boiler. So I think it's golf time now. Thanks. Hope you enjoyed the video. Please comment, like, subscribe and share. Total Output Power Solutions. Thank you.